Okay, enough talk. How big would a modern particle physics collider need to be to smash beyond the standard model? What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a fantastic week and have a wonderful weekend in store. The recent support and discussion on the channel has been absolutely fantastic, so please remember to continue liking the videos if you're enjoying the content and subscribing to the channel. It really helps me out. I'd also like to thank one viewer, Lionel, who has been very generous with channel donations. So thank you, Lionel. Hello. Today, just a quick video. We keep building bigger and more powerful particle colliders, but so far, the standard model of particle physics has remained stubbornly resolute.
Why won't you die?
So I wanted to ask the natural speculative question: how big might a collider need to be to ensure that it would reveal new, never before seen physics beyond the standard model? Let's speculate heavily, you and I, on a Friday afternoon. First, a quick recap of where we are in particle physics. Previously on particle physics. The Large Hadron Collider has fundamentally altered the high-energy particle physics landscape over the past 10 years. The discovery of the Higgs boson in 2012 was a monumental triumph. It validated the prevailing hypothesis for the origin of mass of fundamental particles and illuminated a clear path of study extending into the future. However, for many experimentalists and theorists, the success of the LHC has been bittersweet. The lack of clear signals of physics beyond the standard model at the TeV energy scale has been disappointing. We found no supersymmetric particles. We found no extra dimensions. We found no dark matter. For some, particle physics is reaching a crisis point, and the doomsayers of particle physics are circling. Where do we go from here? The LHC has provided a clear picture of the high energy frontier from data that we did not have a decade ago. There is a Higgs boson at a mass of 125 GeV, but there is then a potentially huge energy gap to any new physics phenomena. A significant vocal minority of scientists believe that particle physics is grinding to a halt, and that building larger, more powerful colliders is not currently justified given the theoretical predictions regarding what we might find. In short, some think that we intend to build colliders for colliders' sake. We do, however, know somewhere where new, beyond standard model physics must exist: the Planck scale, the place where relativity, quantum mechanics, and gravity meet. There are several fundamental constants in our universe. The speed of light is a natural unit that relates time and space in Einstein's theories of relativity. The gravitational constant, or big G, is the constant of gravity that relates mass, distance, and gravitational forces. H is Planck's constant, which relates the energy of a photon to its frequency and arises from quantum mechanics. These fundamental constants tune the nature and physics of our universe. And notice that given their units, they can be combined in such a way that they produce a mass, the Planck mass. The Planck mass turns out to be 22 micrograms, just 22 millionths of a gram. This doesn't sound like very much until you compare it to the mass of known fundamental particles. Electrons, for example, have a mass of 9 times 10 to the minus 31 kilograms. The Planck mass is far higher. This mass can be converted into an energy using Einstein's famous equation E equals mc squared to produce the Planck energy, 2 times 10 to the 9 joules, or 1.2 times 10 to the 28 electron volts. This Planck energy defines the energy meeting point of gravity, quantum mechanics, and relativity, the energy scale at which all must make appreciable contributions simultaneously. Currently, we don't know much about this three-way interaction because gravity is so feeble that its influence on things as small as fundamental particles and quantum systems is immeasurably small. Or alternatively, we could say that quantum effects are immeasurably small for macroscopic objects large enough to have substantial gravitational effects. Most experimental particle physicists like myself have the same reaction towards gravity. However, if we could just squeeze the Planck energy, a billion or so joules, onto some fundamental particles and smash them together, we would be creating particle collisions at an energy scale where the quantum effects of gravity must become apparent, and where new physics phenomena would have to emerge in our detectors. So why don't we just build a collider that operates at the Planck energy and quiet the naysayers of particle physics? Well, it's a little tricky logistically, to say the least. In modern colliders like the Large Hadron Collider, charged particles, in this case protons, are accelerated using extremely high electric fields produced by superconducting radio frequency cavities, and then guided around a collider ring using powerful magnetic fields produced by superconducting magnets. Radio frequency chambers are specially designed metallic chambers, spaced at intervals along an accelerator. They are shaped to resonate at specific frequencies, allowing radio waves to interact with passing charged particles. Each time a beam of particles passes the electric field in the radio frequency cavity, some of the energy from the radio waves is transferred to the particles, nudging them forwards, like a surfer riding the waves. Generating stronger electric fields allows scientists to accelerate particles more rapidly and pack energy onto them more quickly. In the LHC acceleration complex, fields of tens of millions of volts per meter are generated in RF cavities. That means that particles move through a potential of millions of volts for every meter they traverse, and that tens of millions of electron volts, or about 10 to the minus 12 joules, is added to a particle every meter. Generating even higher electrical fields is very challenging, especially within the strong magnetic fields of a collider such as the Large Hadron Collider. However, let's throw practicality completely out of the window, as we see in a recent report from CERN collider scientist Frank Zimmerman, called Future Colliders for Particle Physics, Big and Small. Let's assume that advances in technology allow us to continue to produce higher electric fields and faster accelerating cavities. How many meters of such electromagnetic acceleration would be needed to get particles powered up to the Planck energy of 10 to the 9 joules? Well, you'd want the largest electric field you could possibly generate to accelerate the particles as rapidly as possible and keep the accelerator as short and compact as possible. However, as Zimmerman points out, an ultimate upper limit on the strength of this accelerating electric field and the limit of electromagnetic acceleration of charged particles may be set by the Soter-Schwinger critical electric field of 10 to the 18 volts per meter. The Schwinger effect is a predicted physical phenomenon whereby matter is created by a strong electric field. If we have an incredibly strong electric field, the energy that exists within that field can actually be high enough to start producing large numbers of electron-positron pairs out of the vacuum, according to Einstein's famous equation E equals mc squared. This creation saps energy from the electric field and causes it to decay, capping the rate at which particles can be accelerated by increasingly large electric fields and electromagnetic means. So creating electric fields above 10 to the 18 volts per meter, even higher, is unlikely to be feasible. I've learned never to say impossible in physics. But assuming this electric field limit could be achieved using future technological advances, the Planck scale of 10 to the 9 joules could be reached by accelerating particles through an accelerator with a length of roughly 10 to the 10 meters, or, to make things a little bit more tractable, 1/10 of the distance between the Earth and the Sun. That's pretty hefty, but hey, we wouldn't have to go bothering any other solar systems. And believe it or not, A solar system scale collider at the Planck energy has been previously considered and was judged, I'm not sure how, but it was judged, to be not an inconceivable task for an advanced technological society. So, very Star Trek, or a glimpse into our distant physics future.
Oh, you didn't tell him how long it would really take, did you?
Well, of course I did.
Oh, laddie, you've got a lot to learn if you want people to think of you as a miracle worker.
Of course, it's likely that new technologies, materials, and methods for accelerating particles will arise as our understanding of physics extends and as our need for higher and higher energy collisions becomes ever more pressing. Will the Solar System Planck Collider ever be realised? Unlikely. At least not in a form that we currently envisage. That said, it's fun to calculate some of the limits that our future selves may run into, especially as they kick up some fascinating physics and constraints of their own. Maybe in the future, I'll return to this topic and think more deeply about the road that may exist towards creating colliders that approach the Planck energy. It's certainly a fascinating area. However, for now, if somebody tells you that particle physics is grinding to a halt, tell them that we actually have a really good idea for where the R&D money could go. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.